Thank you very much. My name is Mirela Beloiu Schwenke. I'm a postdoctoral researcher at ETH Zürich in the group of Professor Verena Gries. And I'm honored to give a workshop today together with Elias Berger at the Forestry AI today. So Elias, would you want to introduce yourself?
Yes, I'm here, but I cannot share my video, but I hope you all can hear me at least. Yeah, so my name is Elias Berger. I'm working on my master's thesis at the moment with Mirela on detecting signal tree vitality and mortality on RGBI images. So I'm actually quite new in this topic, but I still hope that you can learn at least some stuff also from my part.
Thank you. So I will continue then. And first I want to thank Walter for the invitation and everyone else organizing this event. And today I will talk about the tree species monitoring in temperate forest using RGB imagery and deep learning. So by the end of this workshop, you will learn more about object detection methods that can help you identify tree species and how to train a YOLO model. So my research develops methods to assess forest functioning from tree line dynamics to drought stress in species and to monitor biodiversity, specifically the development of models for highly automatic tree species identification and health detection. All this in changing terrestrial ecosystems. So I will focus mainly on tree species identification today, as you saw in the workshop presentation. Why does tree species identification matter? You know, it matters to me. I studied this for a long time, but does it matter to everyone? So as we face anthropogenic climate change and extreme climate events, tree species identification is now more important than ever, as it allows us to advance forest monitoring and management. But to better manage forest, we also need accurate data. We need to know how to quickly identify tree species. So we need to have an automatic forest inventories to have better to better monitor biodiversity and even physiological stress. And it's not only me interested in this. There is a clear call for a change in the culture of silviculture by integrated remote sensing data. Here we see only a few papers that present possible monitoring system and how to go from individual stand to near real-time monitoring network, and also that AI basically needs more data. So the question remains on how to proceed. To know how to proceed, we need to know the current challenges and opportunities in detecting tree species. Several papers have addressed this issue and advanced the state of the art. Different data and methodologies has been used. So today, CNN is opening new horizons for the forestry field. For example, although semantic segmentation has been used widely, object detection as well as intersegmentation, what you see in the lower images, can provide a more accurate information and have high transferability. Now, I don't know, you know, how much you know about this. So I will make a brief introduction, but if you still have questions, we can you can address them. So there are different approaches. So we have image classification that is just telling you, you know, it's a tree, is not a tree. We have object detection that is telling you, okay, each single tree and can geolocate the tree, so you know the coordinates of that tree, and it's detecting each single individual. We do have semantic segmentation, which can tell you, okay, there are 2 species in this picture, but it cannot really tell you, you know, can geolocate every single tree. And there is insta-segmentation that unifies object detection and semantic segmentation into a new, more, better approach, where we have the delineation of every single tree and the geolocation. Basically, what you see in this publication from Luminitz, where each single tree species were identified on a street level image. Now, many approaches has been tested in urban areas and also plantations, but yet the question remains whether we can use CNNs for tree species identification in rather heterogeneous forests. So, to answer this question, we gather data for 4 species with more than 10,000 geolocated trees. We use ArcGIS Pro and Python for the data processing and the model development. And then we also downloaded RGB imagery at 10 centimeters for the geolocated trees. The models that we use many models. We tested many models to see which one is the best for our case. And we also tested data augmentation. So the species that we tested in this paper are Norway spruce, silver fir, Scots pine, and European beech. And the forest, you can see that they are just, rather mixed forest with different tree species, images taken from, you know, mostly the summer season, but it's also spring and autumn. So it's a mixture, and the study area was mostly northern Switzerland, where we had the images needed, and these are the test sites that we consider at that time. For accuracy assessment, we use the standard procedure like precision, recall, F1 score, and the intersection over union with a threshold of 0.5. So for those that really want to know the steps, hopefully this presentation will clarify that. So the first step is to gather the input data and pre-process them, meaning that you'll need to bring the RGB or RGBI images and tree species labeling together and create the training, validation, and test set. And this takes, at least for us, took a lot of time. It's very it's very time consuming, I would say. The second part, it's model selection. You can test different models depending on what you aim to do, and then the hyperparameter optimization. In the end comes the accuracy assessment and output, so you can use different option. What we did in that paper and was maybe a bit bold, we did not manually label all trees, because to manually label 10,000 trees, it's a lot. So what we did was we had the GPS coordinates of each single trees. We did check if those GPS coordinates correspond to the middle of the tree, and then we created automatically a buffer. You can create this buffer based on the the diameter, the certain measurements, or you just create a buffer based on the tree species. So we did have a buffer for beech, larger than for spruce, for example, just because after our measurements we realized that the canopy of a beech tree, mature beech tree, is actually bigger than a spruce tree. It was just a more automatic way of creating this reference data, given the time constraints. but I would say that delineation would be the best approach. Yeah, so then more about the model. So in the paper that you saw, we use faster RCNN. So in object detection architectures fall into two categories. One-step algorithms, such as RetinaNet, YOLO, single-shot detector, and two-steps algorithms, such as the RCNN family, faster RCNN, mask RCNN. Generally, one-step algorithms are considered more computationally efficient, while two-step algorithms deliver more precise output. So you have to decide what you want. Faster RCNN, it's a two-step algorithm and has two main components. We see here the region proposal network that generates region proposals where an object might be located, and the faster RCNN detector that uses these regions to classify the objects and refine their bounding boxes coordinates. Now, YOLO runs a lot faster than faster RCNN due to its simple architecture. Unlike faster RCNN, YOLO is trained to classify, to do classification and bounding box regression at the same time. So in our case, at that time, for the paper that you saw, we went for faster RCNN. It gave the best results. So a bit about the parameters. We do have all this information integrated in the paper that we publish. So here is nothing new, I would say. What we did notice, we noticed like the time for training a model vary a lot. If we had one species in the model, so we train a CNN, a faster RCNN with one single species, this took maybe 30 minutes, but if we had multiple species, it took longer. This is not only because of the model, it's also basically on the computer that you have, you know. Yeah, we did have an image size of 250 by 250 pixel. You can vary that. We also did try with others, and you may get different results. Now at the end, Elias will walk you through training YOLO, V8, and you'll see basically more about those parameters. Now a bit about the results. As I mentioned, we train the model for single species detection, basically only because it's run faster, and also people might not have data to train a model with more species. So you are interested to know, if I have only data for this species, is this species gonna be detected well, or do I need to have in my model multiple, multiple species, so the model detects better, a certain species or both of them? So what we could see here is that Norway spruce was the best detected. So F1 score varies from 0 to 1. 0 means that nothing is detected, whereas 1 means that all the trees are detected correctly, right? And when we put all the species together, we did notice that pine was the best detected, followed still by Norway spruce, and then fir, and then European beech. Now, how can we explain that? Why is that the case? Or what can we learn from this? So here is the confusion matrix for single species, and then for multiple species. It looks complicated, but I will walk you through this and try to explain it. So as a reference, so as a geolocated point, we have spruce, and the prediction, it's the model also is predicting spruce because was trained for detecting spruce. Now what we see is that indeed it detects spruce 76, 0.76, so detects spruce. However, there are fir and pine, so there are still fir trees in the reference we see here, but those like 0.04 are detected as spruce. And then 0.02 of the pine trees are detected as spruce also. So what we see is that the model was trained for spruce, but it's misidentifying tree species. So it detects, other species. If we look at pine, the situation is more critical because we do have the model trained for pine. I have to also mention that we did not have a lot of data for pine trees. So also our data set was not so well balanced. That also it's it's not so great. So in the reference data, we had pine, was detected pine, but also a lot of fir trees were detected as pine and beech, maybe due to the tree canopy. Then if we go into multi-species models, what we can see, for example, here we see a lot of zeros. This is basically thanks to the fact that the model is trained with multiple species and it learns to actually, okay, this is this species, this is this species, and is not misidentifying the species because already knows that this is something else. So yeah, we do see the model performance that and we see that the misidentification decreased to almost zero in some cases. However, we do see that we have a lot of false negative that are detected there. Um, in terms of illumination, you might ask yourself, what happens if I want to detect trees on a slope and the illumination conditions are not great? We did do that and we realized that indeed illumination decreases the performance of the models. And also what we notice is that mature forest stands with regular density were better detected than younger and denser forest stands. And this is simply due to the fact that we did not have data from younger and denser forest. So the model was not trained with those data, therefore could not also detect that. Although younger spruce trees may have the same structure, they were way smaller and the model was not trained from that. Data augmentation, it was actually good. I would recommend it. Here maybe did not increase all the time the performance, but I would just recommend it to do it. We also did not do too much data augmentation at that time, but we are now having more options for that. Here it's an example of 1 hectare plot where you see how the models works and how it's detecting. So the ground truth data, so the ground truth are these circles. I hope you can see my mouse on the screen. These are the ground truth data, the circles. And when we have this square here means that was correctly detected as silver fir. In this case, also Scots pine as well was well detected, but we do see that we have trees and that were not detected. This is reflected basically in the F1 score. Here it's another image. It's very interesting to see that even more denser parts of this plot were very nicely detected. So we do see each single tree nicely detected, and we see that in this case the F1 score was higher. So I would say that it varies depending on the site condition, the species composition, the your image that when it was taken. But yeah, was quite nice to see this. And now I won't keep you too long on this. Um, One thing that actually I'm also interested in, it's forest mortality. So there it's questions that we should ask, what will forests look like in the future? And why I'm asking this, mainly because mortality is increasing in most of the world's forest ecosystems. We do see mortality events everywhere, in the Amazon, in the Africa, in the Indonesia. We see it across the globe, and also in regions where it's not, not expected to happen that much. Let's say like that. And this is mainly due to the previous drought events, and there it's expected to have more drought events also in the future. Now about tree mortality, how Franklin put it in the past was created this mortality spiral. So you go from a healthy tree, and through different processes, the tree might die. But there it's also an option for trees to recover over the time. So long story short, the forests are monitored, but often not at tree level. And we need a better quantification of what is dying, where, what is happening, which species are highly affected. We need to better know this and to quantify it. So for that, in some past work and future work is not yet published this, but we are working on that. We are trying to also identify tree vitality and mortality. So basically, to create an automatic monitoring system for single trees and their health. So to unify tree species with tree health. But it's still a lot to be done on this. So I will now hand it to Elias, who will walk you through data structure. And Elias, if you need me, I'm here.
Okay, that's good. I think if you can click the slides for me, then we don't have to switch
Good.
the data share or the video sharing. Yeah, so what I will do now is I will tell you more about the data conversion and the data structure, but it's not used for the faster RCNN, but I also want to show you how to train YOLO V8, which is actually a newer CNN. And first I want to show you a bit more about the data conversion. So when we labeled all the data in ArcGIS Pro, and when you export it with ArcGIS, you will export them as Pascal VOC. And for using YOLO, you need to change the labels from Pascal VOC to YOLO format. It's the same labels, but just another format. You can see on the right is the YOLO format. In the first number is the label. So label 1 was a stressed conifer here, and label 0 were healthy conifers. The second number is the center, the x coordinate of the center of the bounding box. The second one, the y coordinate of the center of the bounding box, and then the next number, the bounding box width, and then the last one, the height. So you have all the information of all the bounding boxes in one label. And yeah, we had to change that from Pascal VOC to YOLO. Then you can click to the next one exactly. Another thing I did, this is now for my master's thesis, is we had to clean the labels. As you can see, ArcGIS, when it exports your images, it cuts them into those tiles. I used 320 pixel to 320 pixel tiles, but it also just cuts your bounding boxes. And you can see there is a blue bounding box right on the edge. And I also showed this bounding box and label above. And what we did there is we cleaned those bounding boxes. So the really small bounding boxes, we just delete them. We drop them because later on YOLO would have problems with detecting those trees because it can see like almost nothing. Yes, so this was the label cleaning. And then what I did for my thesis, but what I also will do for the example later on, is we used some masking, because you can see we have some plots for my thesis where I didn't have enough ground truth data because I had vitality assessments, and yeah, there we didn't have any ground truthing. So we just used masks. We took our bounding boxes and we applied a buffer of half a meter to it, and then we masked everything around it, because otherwise the YOLO network would be like confused when there is one label tree and then it detects another pizzeria tree, but there it has no label, so it detects it as a false negative, I guess. Yeah. The next thing is that YOLO V8 at the moment only accepts 3-channel images, so we had to drop our infrared channel for now. And then the last thing on the next slide is that YOLO only accepts 8-bit resolution images, so we changed images from 16-bit color depth to 8-bit. Yes, so this was all the preparation for the labels and for the images. And now on the next slide, you can see the folder structure. YOLO V8 only accepts this folder structure. You have one, your main folder in gray, and one folder are the images, and the other one are labels. And you can see that within the images folder, I have those subfolders for several test folders, several train folders. And this is also really nice because you don't have to merge all those folders together first, but you can take a folder from a colleague of yours and just drop them there. The only thing you have to keep in mind is that for the labels folder, your subfolder needs to have exactly the same name. So you see in the images folder, you see that there is a test Germany folder, and in the images folder, yeah, they both have exactly the same name. And what you also want to drop in your main folder, what you can see on the right already, is this YAML file. And there you can see this is a file where you can indicate the names of your labels, like 0 was a healthy conifer. Then the next one is the path to your folder. YOLO needs this path to also find the images later on. And then the next thing is the listing of the different subfolders. And there you can see that you only need to list the image folders. So you see the train, and then you see images train Germany and images train Switzerland. And YOLO will find the labels folder by itself if you name the tests, if you name the images and labels folder with the same name. So when you have this YAML file, it works perfectly nice. And now I try to share my desktop. Let's see if it works. Can you see my screen?
Nope.
Not yet.
Not yet. So maybe then, Mirela, you have to show the screen. Or share the
give me a
computer.
second. Yeah.
Yeah.
I'm opening that. So second, share screen, share. Okay.
Perfect. So now you see the computer. Now I want to show you some hands-on on another data set. This is the data set which Mirela used in her paper, but we have additional tree species in here. You can see the YAML file here with 8 different tree species, or just Helia, for example, then the path. And here are the folders. As you can see here, I only have one train, validation, and test folder. And then here are those folders. You can see in the test folder, for example, is the picture 2209. And also in the labels, in the tests, you have this label, as you can see here. with exactly the same name. This is also important. And this is everything you need from the folder structure. And then you can go to a script where you
Sorry for
import your...
interrupting. Can you expand the screen of the RStudio?
This a bit bigger. Don't
Can you
know.
make it bigger? Okay, that's the biggest. Okay, that's fine.
Yeah, that's the biggest at the moment. Maybe we can increase the size a bit. Or with a shortcut. But it's okay. I hope that you can see at least a bit something.
Well, it's better.
Okay, good. Perfect. Thank you for telling me. So first, we import the packages like PyTorch and YOLO from Ultralytics. Then I always check if the GPU is available, which is true. And then I empty the cache to make sure that the GPU runs perfectly. I always create some folder and subfolder for the output. You can name them. I always do it as a variable, as tutorial is the folder name and species is the subfolder name. And now here in the next line, you can write down which model you want to train. And YOLO already offers you some pre-trained models, pre-trained on the Coco dataset. And you have several sizes from nano to the extra large one. And now for this exercise, I used the small one because we didn't have really big data sets. So I used this YOLO V8S. And then this is all the code you need to train your model. You load the model here with the model template I used before. Here you set the model to the train mode, and then you indicate the YAML file where the path to the YAML file, your subfolder name, folder name. Now I also wrote down that it should save some plots for me for the training. I said that it should train for 500 epochs with a patience of 80. So when after 80 epochs, 80 times it looks through the images, no, it looks 500 times through the images, but if we have no improvement after 80 times, then it stops the training. We have the batch size and the image size. Yes. And we can adjust those also as different hyperparameters. Now here I only used a different optimizer. I set the seeds. I set the learning rate to tell the model how fast it should like make adaptations. But you can use so many different hyperparameters, and it's all indicated on the Ultralytics website. When you go to the train mode, you can scroll down, and here you can see a list of all the hyperparameters you can use, and with default values, yes, it's really handy to use. What's maybe the most interesting is here the data augmentation options. You can see I set the translation to 0. The translation is that it shifts your images horizontally to left or right. And when we do that, we might lose some trees on the edge of our image. So I set it to 0. We can do some flipping if it should erase some parts of the images, brightness, saturation, etc. So you have a lot of options. And I already ran this model, and it took 105 minutes. For the whole data set. And in the end, you get a folder with all the outputs, which is also really handy with different, like the confusion matrix you saw before in Mirela's presentation. And other, I don't have time to explain all of that, but you get a lot of plots to have a look how your training went. And maybe the most interesting is the model in the end. You have the best model and you have the last model, and you can like copy the path to your best model, and then you can evaluate your model. Because now we only use the training data set and the validation training set to observe the model. And now we want to use our testing data set, which we set aside, and want to see what happens if how good our model is. And we import the packages again, and also empty the cache, create the folders. Here I can put the path to my best model, which was already there. Here you can also set some hyperparameters. Maybe the most interesting ones are the confidence threshold. So you can say at which confidence, how confident your model should be to create a bounding box. And then the NMS, YOLO says it's an intersection over union. It's not really the intersection over union, it's the non-maximum suppression. If you have multiple overlapping bounding boxes created, you can filter the worst ones out. Yeah, so this you can do here. And then you can also run this and you get this table where you can have a look at your whole model. We get a mean average precision of 83%, which is quite high, but we also have only masked images. We also have the mean average precision or recall for each different each single class. And also here too, I told YOLO to save the outputs. It also created this nice folder for me with the different plots. Here you have, again, the absolute values. Here you can see how your model performed, and it doesn't look too bad except for Quercus and Arzo. Yes, and also you get the different outputs. Maybe one output which is quite interesting sometimes to have a look at is the plots. Here you can see the resolution isn't too good because we're using a remote desktop. But you can see this is the original bounding box, and those are the bounding boxes created by our model. And you can see we have double bounding boxes still here and here. And so we still would have to clean them even if we have the NMS. Yes. And now, last but not least, maybe interesting is how does our model perform on a full image? I chose one image here with different trees, and I took this image path and put it right here. I loaded the model again, and then we can tell YOLO how big the image is, if it should save the plots, and also you can save the bounding boxes as a text file. Also here you can set intersection over union and different stuff, but this is the most interesting stuff, and you see it needs like 1 second to give you a plot, and this plot is now saved here. And now for this example, it doesn't look too bad. We had worse examples, but here you can see how fast you can train a model at the moment, and here you would have the labels. So I hope it wasn't too fast, but I still hope that you had some that you learned something from this small introduction.
Thank you, Elias. So maybe one thing to mention for the entire community, we did publish with the first paper the data. Yet, yeah, the data, I mean, we improved them a lot, and we plan to publish a second version, as I actually mentioned also on Zenodo, that will be published another version. So I ask a bit more patience for those that requested the data, as we'll upload a new and a better data set. And just to know what we have there are not the R scripts or the scripts per se, the CNN models. We do have only the weights of the model there. So you are not missing much on that, on the scripts part. And YOLO, we wanted to show you YOLO here because the package from Ultralytics is super developed, and you can actually implement this if you want. So thank you. We probably can start with some questions.
Yeah, thank you, Elias and Mirela, for that really great talk. I'll be focusing, as we alluded to, on the tropical regions, which have their own kind of unique set of challenges. Just a quick introduction. So I did my PhD here at Cambridge with Professor David Coombs, and I was helping to kind of develop these technologies. So looking at how we can apply deep learning to kind of imagery of tropical forests and extract useful information from that. My background's in physics, and I've kind of turned towards ecology. So I feel that gives me some good skills when it comes to the kind of coding and more technical side. But yeah, and I really got into the ecology through my PhD and enjoyed climbing the trees more than anything, I think. So just a quick overview of what I'll be covering. So sorry if there's any overlap with the previous talk, but I'll be talking a bit about why do we want to map individual tree crowns. And then I'll show you a little bit about our tool, Detect Tree 2. And then I'll go through and do, as was done in the previous talk, just look a bit about how you can kind of use this tool and generate some results. And so if you have Google Colab, feel free to open that up if you have a spare monitor. And yeah, you can find Detect Tree 2 on GitHub. Don't forget to give it a star, but you can also install it and play with some of the example data that we have listed there. So this is just to give you a flavor of our forests and the view we can get from above. I think everyone here knows the kind of unique vantage point you can gain by using satellites, planes, but in our case, we've been using a lot of UAV imagery. So this was over Nurag in French Guiana. I was also working at Parakou in French Guiana, and these sites are very carbon dense and hyper diverse as well. So there can be several hundred species within just a single hectare of forest there. And so why do we as a tropical ecologist, I'm interested in kind of mapping the canopy for several reasons. So using UAVs or other aerial forms of imaging, we can increase the speed and scale of inventories drastically. And this can help either for kind of ecological studies or kind of commercial applications. You can understand better the carbon dynamics of the forest, so you can detect tree mortality. With the right tools, you can even infer sort of tree growth. And yeah, understand kind of how the kind of these carbon pools are changing through time. If we can not just kind of find the individual crowns, but also detect species, it will help us to understand patterns of biodiversity that we see. And in my particular case for my PhD, I was monitoring the phenology of tropical forests. So in temperate regions, we can see quite clearly what's happening. You know, in autumn, all the leaves fall off, and in spring, they pop back up. Whereas in tropical forests, there's a lot of variety. So there's a variety between ecosystems, and then even within those ecosystems, there's a lot of variety between trees. So some trees will shed predictably every year, some every other year, some more frequently, some are very synchronized, some are very asynchronous. And so this is one of the things I was trying to understand. And yeah, this is why we wanted to kind of really map the tree crowns in our regions of interest in detail. So this is just to give you an idea of what the forest might look like from above. So this is just an RGB imagery, but we've kind of played with the colors a little bit to exaggerate the contrast between the different species here. And what we've done is we've gone in, we've delineated all the tree crowns in kind of the forest plots in which we were studying, and we've provided them with a species label. And this was done by matching what we could see from above and what we were seeing from below the canopy, and matching the crowns to the inventory data. So that was kind of generating our training and testing data of these individual tree crowns. And yeah, as Mirela said, it takes a long time to do manually. So we really wanted a way of speeding this up and to provide a tool that other people could also use to do the same kind of thing. So the code base that we decided to borrow from was Detectron 2. And so this was built by what was Facebook AI at the time. It has now become Meta AI. And it uses a CNN type architecture, and in particular something called mask RCNN. So not only do you kind of detect the objects in the image, but you can kind of delineate them. And as you can see here, typically, you know, Facebook, you're dealing with just day-to-day images. And so their models are trained to find people, bicycles. You can see it can kind of detect trees here, but actually when we take just their baseline models and show it an aerial image of a forest, it doesn't recognize it as tree. It thinks it's broccoli. So we had to take their train models and then train them some more with our own data, so it would stop thinking that the forest was broccoli. And so I'm not going to go into all the nuts and bolts right now of kind of how it works, but that's to say you can check out the repository and you can check out the article. But just briefly, what you do is you show it the RGB images, the aerial images, you show it the kind of the training polygons that you've generated, and through a process of showing the network these images over and over again, it will kind of learn how to replicate the human delineator and then start to do that automatically. And so you can show a relatively small amount of area that humans done, and then it can scale that up very rapidly, and you can kind of delineate all the trees and find where the trees are in kind of vast tracts of forest. As with Mirela, it's quite common practice. We say we've got a correct match when the kind of the IOU between the kind of prediction, the predicted crown and the test crown is more than 0.5. But this is a parameter that you can adjust. We went a bit beyond this, so we were very lucky with so Project Phenobs is the project I was working on for my PhD. So it's a phenology project, and we were taking imagery every 3 weeks, and we wanted to see what the effect would be of actually combining predictions across time. So instead of just taking a single snapshot, how can you kind of combine the kind of AI predictions across multiple dates, fuse them together, and can you generate a more accurate map by doing that? And so that's just an example of the different time steps. And what happens is you get it to predict on a single date, and it does a pretty good job. But then you get it to essentially keep predicting across multiple dates, sort of 7, 8, 9, and then by combining all those predictions and fusing them and taking kind of average shapes within given areas, you can generate like this, a set of crowns across a forest region. And here the different colors kind of hint at how sure we are about these predictions. So the kind of the bright ones here have had lots of matches across dates, and then the darker polygons are ones where there's kind of fewer matches across dates, so we're slightly less sure. But it through this process we can build up quite a full picture of the trees within a given area. And so this just highlights that. So if you look at this plot here, on the y-axis, we have the kind of the F1 score of the models. So that's an F1 assuming a 0.5 IOU kind of matching criteria. And essentially the blue line at the top, that's the kind of the model trained on the most dates of data. And the red one is actually the model trained on the least dates of data. But what we see is, the more data you train on, the better model. But also, if you look across the x-axis, this is the number of dates that we combine together to generate that final output. And if you just have a single date, your accuracy here starts below sort of 0.7 F1 score. But if you combine sort of up to 9, 10 dates, you're above sort of 7.7. Around here, so getting close to 0.8. So you see a substantial increase in accuracy. So if you have the luxury of having multiple dates of data, it's very worthwhile to try and kind of combine the information across dates to get an accurate map of your landscape. And so because it's so diverse, we can't just dive right in and try and use the kind of the RGB images or even the multispectral images to try and predict species. And so what we have been using is in fact hyperspectral data. So you have several hundred bands. When you kind of fly over the forest, you're collecting data across several hundred bands. And this gives you, a spectral resolution that kind of allows you to begin to infer what maybe the kind of the chemical and physical properties of the different trees are. And what we can see here is when you kind of standardize the spectra of different species, you get what we call kind of spectral signatures. So each species will have a kind of slightly different kind of spectral standardized intensity across its spectrum. And this allows us to start classifying a lot more species essentially than we might be able to do with fewer spectral bands. So at the moment, we're pretty happy with how it's doing. So we tried 178 species, and that was just used basically all the species where we had at least 2 examples, one in which we could train on and one in which we could test on. Yeah, we think 64 of the species, the more common ones, we do quite well. And that leads to about 70% of the tropical forest area being mapped accurately. But I should just make it clear. So the detectory 2, the tree crown delineation and the detection is separate from this. We can kind of combine the products, but it's actually more kind of fundamental machine learning that proves to work better on this high feature hyperspectral data. So in fact, LDA, linear discriminant analysis, quite a straightforward machine learning tool, actually works best for us when we're trying to classify the species based on this hyperspectral data. And that's what the final crown map looks like. And in the background there, you have kind of a representation of that hyperspectral data. So it's just kind of collapsing the many bands down into 3 bands, just a red band, a green band, and a blue band, just so we can inspect it. But it just highlights the kind of the contrast between the different crown types that we have in our region. And then from that, like I said, phenology was something I was particularly interested during my PhD. So when a tree's shedding their leaves, when a tree is flushing their leaves, how do the leaves kind of age through time? And then the idea is to link this to kind of the fluxes that we observe in the forest and understand the kind of photosynthetic activity present in the forest through the year, see how it changes. This is something we can't really represent well in existing kind of dynamic global vegetation models. So kind of unpicking it at the individual level is really critical. And so, yeah, what you can do is when you've found the trees, delineated them, and assigned a species, then you can start to understand the kind of phenological patterns that we observe. And here is just a nice crown where you can see it sort of aging and then a leaf shedding. And then actually there's one branch in this tree that's sort of slightly ahead of the rest, that flushes before the rest of it. And then you get the nice kind of bright green, fresh new leaves. And it's around this time, just after they've flushed, that they are kind of most efficient with their photosynthesis. And as they get older, the efficiency of that photosynthesis decreases. And so given that we can kind of map lots of different species and map all the individuals, we can start to kind of inspect how these different species are changing through time. And so I'll try and go slowly on this one, but if I don't explain it quite right, do jump in and let me know if I need to explain any more. But here we have the species names, and this is just examples of the more common species. And what we have with the x-axis is the dates. So this is the period over which we were scanning. And like I said, we have scans every 3 weeks. And then we can calculate for each crown, each time step, like a greenness intensity. So how kind of fresh are those leaves? And what we see is the bright kind of yellow colors are kind of where the freshest, newest leaves are. And then the darkest colors is where the leaves have kind of senesced and even shed. And so what you see with some species, so we can see Rhacodocylon speciosum. I don't know if my mouse is showing, but it's in the 5th column, second row. You can see the bright colors there are all aligning quite well. And then those 2 dark lines in the vertical of a dry period. And so what you can see is the trees of the individuals of this species, they're kind of flushing and then shedding fresh leaves actually during the dry period to really kind of maximize the amount of light that they can intercept when actually there's fewer clouds in the sky. And so this species is quite synchronized and quite clear with what's going on. And there's some species that are quite sort of well behaved like this, and then other species are much more difficult to interpret and a lot more kind of stochastic and random in how they're kind of flushing and shedding their leaves. And so this was the kind of the eventual application of the crown maps that we were that I was developing during my PhD. And so this just gives a sort of summary of how you might be able to apply this kind of crown mapping approach. And so if you have hyperspectral data, you can combine the kind of crown mapping with a kind of species detection and do kind of these species maps across quite diverse landscapes we found. What I'm actually working on now in my postdoc is trying to see if we can extend our kind of tree detection method, like Mirela has done, to do kind of multi-class prediction, but use the multispectral. So introduce that kind of extra band or two of infrared information to see if we can start to predict maybe key groups of species, maybe to the genus or family level. I'm actually working in Sumatra now, and what we're really interested in is the dipterocarps. So being able to find the dipterocarps, and when they sort of return to forest that's been kind of logged and damaged in the past. Then what we showed in our original paper is that using kind of LiDAR across 2 dates combined with these crown maps, you can get a very good idea of the kind of mortality and growth in these tropical landscape regions. So the LiDAR gives you that very like clear, nice depth map. And so growth is quite difficult because it's very fine changes. So you need to be able to have LiDAR across 2 different dates that is very comparable and very well calibrated, which is a lot more difficult to do than it sounds. But then mortality is a bit more easy to understand because it tends to be quite a sudden kind of drop in tree height. And then what you can do with a multi-temporal, well, in this case, the RGB that we showed, but also with the multispectral, you can have some other sort of slightly more refined indices. You can really study the phenology of the forest, down to the individuals, and start to think about how are different species behaving, why are they behaving in this way. I don't have time to go into all that analysis for this talk, but this is the bit I find actually most exciting. But if you want to see, so just in the bottom right here, I think most of you, well, some of you may have heard of Deep Forest, which was a fantastic tool. You know, it was kind of the first of its generation. But Detectory 2, by this kind of independent team of Japanese researchers, has been shown to be more effective in being able to kind of detect these trees in this case in a temperate Japanese forest, but very dense, closed canopy forest there. What's the time? I think it's okay. And as I said, this is the kind of a future direction for Detectory 2. So we're looking at multi-class problems. So like the species mapping in Indonesia, seeing how far we can get with these diverse landscapes, because it is a logged over forest. It's not as diverse as, you know, these Amazonian forests that we were looking at before, but it's still a major challenge. But hopefully by introducing additional spectral bands, we might be able to make some progress. Where we've been making some progress already is with liana infestation. So lianas really impact the carbon dynamics of tropical forests. I'm sure anyone who's been to a tropical forest or a rainforest has seen lots of different infested trees, and it's predicted with climate change that infestations will probably become more prevalent, which is likely to cause more mortality. And so understanding how these infestations are spread and how they're changing through time is really important. And what we've been able to show is not only can we kind of find the tree crowns and delineate them, but we can start to predict how infested are these tree crowns with the kind of the lianas that we see. So started with the just binary problem of a kind of, do they have a clean crown or an infested crown? And then kind of break that down into kind of severity of infestations. But yeah, the challenge here, as it is so often with these kind of deep learning problems, is the quantity of training data. And so we've got a few sites where we have the tree crowns graded by the level of infestation, and we've made some progress, but in an ideal world, we'd have many more sites on which we could kind of test and see how transferable the models are. And then the last thing within this kind of multi-class idea is to what I showed you before is we had an index showing the kind of the greenness of the crowns through time. So suggesting when there's like a green up or a flushing of leaves and a shedding of leaves, and showing the kind of the aging and senescence of leaves. But something that would be really nice to do is to be able to automatically detect the phenophase of each of the trees. So for example, you know, leaf off or shedding, flushing events, but also maybe even flowering events. And if we have high enough resolution data, maybe even stuff like fruiting events. But that, yeah, still a pipe dream, and again, requires a huge amount of very expensive to label data. So maybe I'll slow down slightly just to give people who are interested and do have a spare monitor available a chance to, if you want, try and download the data. We have a tutorial that you can actually do in your spare time, and I'm going to go through some parts of that now. But yeah, what I recommend is Google Colab for this. So a lot of the work we've been doing, we actually use the Colab Pro option. So it's a bit annoying to have to spend a little bit of money each month on a subscription, but the ease with which you can kind of access GPUs and play around with different packages, and it's really fantastic. So that might be available to some people, but might not be available to other people. Question no. So it should be quite easy to install. So it's just off the GitHub repo, and yeah, like I say, Colab is the most straightforward one to use. If that's not available, Linux is probably easier. So if you have a kind of Linux device with GPU, that's good, or kind of Linux clusters as well. We've tested it on a few different clusters, and so yeah, Windows is possible. I know some people who have used it on Windows, but it's a bit more painful to get everything set up and all the kind of libraries correct for that. And as many of you will know who've used a lot of kind of geospatial packages, the kind of a GDAL can be one of the major issues here. So making sure that that's kind of set up and the headers are all pointing in the right places is super helpful. And then otherwise you just need Python. It all runs in Python or notebooks. But you do need to have kind of PyTorch, Torch Vision, and Torch Audio already set up. And then what it does is it pulls in, so Detectron 2, which was that kind of Meta AI library, it pulls that down. And then we've got our own kind of functions that essentially allow you to hopefully quite easily go from end to end. So essentially at the start, you just need geotiffs, you know, some kind of geo-referenced image data, and then a shapefile or a geo package of your tree crowns. And with those two things, we've designed it in such a way where it's quite straightforward for people just to kind of point to where those are in the system. And then we've got all the functions that will do the in-between steps, but I'll go through those now. So yeah, these are the key steps I'll talk through. There is one step that is missing here, that is the model evaluation. And I don't want to suggest that that's not an important step. It most definitely is. I don't really have the time to go through that right now, but if you're interested, there are some notebooks on the repo, or you can get in touch with me to talk about how we evaluate the models. But it's similar to what Mirela described in terms of evaluating, you know, precision, recall, F1, to understand how well your model's doing. And then yes, we'll go through these steps to kind of getting towards making these large landscape level crown maps. So this is the folder structure that you'll want. So if you're just working on one site, you'll just need one of these, but here I've just given the example of two different sites. So Danam is a site on which we worked in Borneo, Malaysian Borneo. And then Parakou is that site that I was showing you before in French Guiana, so Northern Amazon. And this is where I did most of my PhD work. And so what you can see here is for Danum, we have the RGB TIFF image, and we have the crown map in GeoPackage. I prefer GeoPackage just because it's a bit more modern than shapefile, and you don't unexpectedly get column names being changed due to unusual things on the system. And then in Parakou here, you can have even multiple dates of data to essentially allow for more training data availability. And so, yeah, this is the initial setup. So you need the RGB in a folder and the crowns in a separate folder. And so the first step is to tile the data. So you can't just input huge multi-gigabyte TIFFs into these networks all at once. You need to kind of break it down into sort of manageable chunks. And so typically we recommend sort of tiles of about 100 meters by 100 meters, and maybe a resolution of sort of 3 to 5 centimeters is optimal, but there's definitely flexibility to have lower resolution. So sort of 30 centimeters is fine. If you get lower resolution than that, then it sort of does start to degrade a little bit, but there's ways of dealing with that in terms of the data augmentation. So one of the data augmentation steps that we found very useful is an algorithm that essentially upsamples and downsamples your images. So makes them kind of fine resolution and just by interpolating, but also makes them lower resolution. So you can kind of get the network used to seeing different resolution images just through an augmentation step. But well, yeah, so this is how you kind of set up the tiling script. So you can see the functions being called in there at the top. You can just see some paths being set to the site path where the image is kept and to where the crowns are kept. And then just using Rasterio to read in the image, and GeoPandas to read in the crowns. And just being careful that your CRS is set to a UTM one. So one where you can kind of measure in meters up and down, so and not a kind of global GPS type CRS. Typically we like to have a buffer so that we're making sure we're capturing trees that are on the edge of tiles, and then within that you set a tile width, a tile height, and because we like most of the time we're working with closed canopy systems, we tend to set a threshold but make sure we're not accepting tiles that are very, very sparse. So it may be when you're kind of labeling your region, you have some places where you have very dense labeling, and this is actually better for training. But if there's places where there's very sparse labeling and a lot of the trees are not labeled, then in general, we want to sort of discard those tiles because it would teach the network to kind of predict just a few trees where actually there are many trees. So this is why we set this threshold here. And so this is just set to 60%. So this is each tile should have at least 60% coverage of tree crowns. Then there's just some bits about sort of naming the files and the outputs. And then we just have a function here, tile data train. So this is tiling the data in a way that is good for training. It's acceptable for the training algorithm essentially. And then this to train test folders, this essentially breaks the data up into training tiles and test tiles. So if, as you want to test the accuracy of your model, it's good to withhold some data completely. So not let your network see any of those tiles in training and then see how well it does on those other tiles in testing. So we can split between train and test. And we also do like a k-fold structure as well. So within the kind of a training data, you can break it into, well, here 5 folds. And so when you're kind of tuning your models, you can train on 4 of those folds and then kind of validate on one of those remaining folds and improve your tuning without exposing the test data. And yeah, this just illustrates how the data will look kind of when it's chopped up. And then after those steps, this is the file structure that we should arrive at. So as before, we have the RGB image, we have the grounds, but now we also have a tiles folder. And within the tiles folder, we have a train and test folder. And within the train folder, we have different folds. And these different folds, again, this is for tuning our models in such a way that doesn't expose the test set. So we get reliable final test set accuracies. Typically, it's good to just inspect our tiles and see how they look before we start the training. There's always a potential that you've misentered, you've entered the parameters incorrectly, and maybe it hasn't tiled as you expected. So it's good to just check before you get going. And this is what this little chunk does here. So you call in some data visualization from the original Detectron 2 library. And you can kind of inspect, if you're using a notebook, just how the different tiles look. So always good to check that before training. And so once you've tiled up the data, you're happy with how it looks, you've checked how it looks, it's time to train the models. So the first step would be to register the data. So it may be that you want to train a model on different sites. And so here I've given 2 different sites. So we've got the Danum site and the Parakou site. So we've kind of, tiled the data for each of them. And if you have one site in the Amazon, one site in Borneo, hopefully the final model will be a bit more robust and transferable rather than just training on a single site. So the more different sites you can train on, the better. Then you select a base model. So if you remember towards the start of the presentation, I said, if you show the base model forest from above, it thinks it's broccoli. Well, now it's the time that we can change that perception and show it how to find the individual trees. But we still want to call in one of these base models because it's this transfer learning, this learning on models that have seen a whole wide range of different data, but just not data from above. They've already learned how to kind of see different edges and shadings and different patterns, the low-level features that will then make it easier for us to kind of transfer it onto our different task. So we can call in that base model. We can set up our configuration. What might be helpful if you're using this on your own forest is to take one of the models we've already trained on our forest. So you can just take that model and try and make predictions straight away, and maybe it will do well, maybe it will do terribly because it's a completely different type of forest. But you can also train from a model we've already produced. So this is like a kind of another step along in a transfer learning. So we've trained initially with this base model, and then we've done some training, but then we've provided our models on Zenodo. So you can kind of just grab those very easily, and then you can kind of insert that into your configuration. So your model will have updated from that original Facebook model to our kind of level of model. And hopefully that means it will be able to learn your context more quickly. Or if you don't have very much data, hopefully it will be able to transfer just with the limited training data that you might have. And once that's all set up, it's quite straightforward to get things training. And what we've included in our trainer is a patient. So essentially, if the model is failing to improve its accuracy after kind of, in this case, sort of 5 epochs, it will stop there, not waste any more time, and just save the best performing model at that point. And yeah, we kind of provide the setups and tutorials with our own parameters that we found through some tuning work best. But there's no guarantee that the way we've tuned it will be the best for your setup. So it's always advisable at least to test, different learning rates and see if your accuracy is very sensitive to any of the parameters. Because yeah, it might be different to what we found. And so once we're all done, we've tagged the data, we've trained a model, then it's time to make landscape level predictions. And so again, we've provided a whole set of functions to help do this in just a few steps. And so we call in those functions here. And again, we point to the image we want to predict on. So this orthomosaic here, and here I've given a different site. So we've trained on 2 sites, and now we're trying to predict on maybe an unlabeled site, see how well it does. And then we want to train the data. So similarly to how we did with the tiling in the training step, we tile up this data, but in this data we don't discard tiles, for example, but don't have enough coverage. So we keep all the tiles because we want to combine all those tiles into the final landscape level prediction. But we do still want to have a buffer, because there may be trees on the edge of these tiles that are being cut in half if we don't include a buffer. But what we can do is, if we can include a buffer between tiles, then we can kind of look at the predictions across those different tiles and combine those into a tree prediction instead of chopping trees in half. And again, we can either we've trained a model as with the previous steps, or we can just take one of the existing trained models, set up the configuration. And again, we just have one simple function here to predict on those tiles, so we've chopped up the landscape. Now we can predict on those tiles. Once those predictions have been made, you need to kind of convert it back into the geospatial. So we start with shapefile and geopackage, and we want to end with shapefile and geopackage that's well georeferenced. And so you take the data that's been predicted from a network and you convert it back into the geographic form. So here, the GeoJSON. And then once you've kind of converted all your predictions into the geographic form, we want to kind of weave all these predictions together, stitch them back together. So they're in lots of tiles, but we don't want, lots of blocky data. We want one kind of harmonious final crown map at the end. So we stitch everything back together. But what happens when you kind of stitch everything back together, stitch all the tiles together, sometimes you have lots of like overlapping predictions in where we had the overlap in the buffer. And so it's necessary to just do one more step, what we call the cleaning crowns. So this algorithm essentially goes through your predictions and it kind of gets rid of ones that in a given area there's a more suitable crown. So one of the nice things about the architecture of this network is it gives a confidence score to each prediction. And so one thing you can filter by is how confident the network is on the predictions. So for example, 0.9 would be something we're pretty certain about. 0.1 would be something we're less certain about. And if there's a 0.9 confidence and a 0.1 confidence shape in the same area, the 0.9 confidence shape will be selected. And so once you've stitched the crowns, cleaned the crowns, in general, the predictions are kind of, they have vertices kind of around the pixels. So it's a large number of vertices, and often that's unnecessary, and it takes up more space on your system than is necessary, and it means that further processing might take longer. So in general, we simplify things down. So we just take a basic kind of simplifying algorithms provided by GeoPandas to kind of, in this case, get segments of 30 centimeter resolution. But this is something, again, all these parameters can be kind of adjusted and adapted for the needs that you have for your final output. And then once it's done, again, you can kind of inspect the data, and if you're ready, we can save an output file, and we can have a look at how it looks in the end. So if it's all gone well, you should be able to generate a crown map like this for your site. So you can count the number of crowns, and again, like I said earlier on in the talk, you can use this crown map for studying phenology or growth, mortality. There's infinitely many problems it can be applied to. But this ability to kind of locate and delineate these canopy crowns very quickly over large areas, we think is a very helpful thing. And hopefully you have some time to use our example data to test the algorithm and see if it can be helpful for the things you're looking at. And yeah, that's all. Thank you for your time and attention, and yeah, of course, thank you to everyone who's supported me throughout the PhD and now onto the postdoc. there's my contact information. And yeah, hopefully you have some questions and points of discussion.